Okay, example number 4, and this is a particular good one for us to be doing at this stage in time, okay, because of a number of things. One, it's a optimization problem that is to do with measurement. Now, this is a really common thing or theme that you see right through past HSC exams. The next reason that's a good one for us to do at this stage is that, unlike the last question that we had to do, there's no A, B, C. There's no scaffolding or steps in place that will help us be led through the question. We have to do all of that thinking in this one by ourselves. We're asked to optimize it, and we've got to go and do that. No helpers. All right, so let's have a look at this question. It is that volume one. All right, it's finding the volume of a pond. And we're given that volume function. And even so, this is a bit of a larger or harder function to work with, highest power being h to the power of 3. And that h, we're told, is the depth of this pond in meters. Okay, so that's putting it into context for us. Here's what the question asks us to do. That verb says find. So again, numerical answer, finding it, getting a value, okay, and it's asking us to find the maximum. All right, extra importance, this word. It is the word of the problem. It's asking us to find the largest figure, and it's a maximum volume of that pond. Okay, so straight away, we're thinking about max stationary point. All right, that's what we want to find. We want to see if we can find that maximum value or maximum stationary point for this pond. All right, because we want to create the largest pond that we possibly can. All right, as per normal, I'm going to go make my functions list now. So then I can purely concentrate on just thinking about my problem and not have to worry about performing calculus skills throughout that process. Okay, so here's my list sitting at the top of my page so that I can go and use it and use any of those 3 functions depending on what I'm trying to do later on in the problem solving process. Okay, we paid close attention to that word maximum. I gave it the double underlining. It's the word of the special word of this problem. So we need to go and start putting ourselves in a place to find a maximum stationary point. So to do that, we need to go and find the stationary points for this problem, all right? And we know we do that when the first derivative is equal to 0. We're going to solve for that. So 0 is equal to 6h squared minus 24h plus 18. All right, so we've got ourselves a quadratic, so we're going to probably expect to get 2 solutions. All right, so this is going to then make the next part of that process of finding the maximum a little bit longer this time. Okay, let's get rid of that factor of 6 that plays right throughout this question. Whoops. So that we can then go and solve this quadratic a lot easier. All right. So we're going to get ourselves 2 answers. When we factorise this one, h minus 1 is going to be equal to 0, or h minus 3 is equal to 0. So our 2 solutions for this particular problem is h is 1, or h is equal to 3. Remember, h being the depth of the water in this pond, 3 meters and 1 meter. Okay, so we have our 2 solutions from that previous step, our 2 points where we have stationary points in this curve or in this function. H is 1 and h is 3. What we're going to have to do now is go and do a little bit of work where we go and find out whether or not each one is in fact a maximum or minimum turning point. So to do that, remember we've got to rely on that second derivative, all right, being 12 lots of 1, or 1 being h, minus 24. Or in this case, when h is 3, 12 lots of 3 minus 24. Okay. When h is 1, we're getting a negative answer. Magnitude of the answer, not important. The fact that that second derivative is less than 0 means we've got ourselves a concave down. All right? That means maximum. In this case over here, when h is 3, we're getting ourselves a positive value of 12 greater than 0, meaning we've got a graph that is concave up at that point in time, which is going to give us a minimum value of that graph. All right, so now that we've done our little work with our second derivative to determine the nature of those stationary points, the one that I'm going to use from here out is this one here when h equals 1, because it's giving us a maximum value answer. All right, now question in this case is asked for the maximum volume of the pond. Okay, since we've found out the depth of this pond is going to be 1 metre to produce a maximum volume, we now just have to go and find out what that maximum volume actually is. So to do that, all we're going to do is substitute back 1 for the height of the or depth of the pond back into the original function and find out what that numerical value really is. All right, that's going to give us a value of 58. All right, so if we're thinking about our curve sketching from before, we have a maximum at 158. And to answer our actual problem, the maximum value of the pond is 58 cubic meters. Done.